mineral engineering, mineral economics, and is affiliated with CSM Center for Space Resources. Next person is John Mankins, who is the president of Artemis Innovation Management Solutions, LLC. His 25-year career at NASA ranged from flight politics and project missions to systems-level innovation, advanced technology research and management development. Mr. Mankins was a manager of Exploration Systems Research and Technology with the Exploration Systems Mission Directorate and responsible for $800 million annual budget involving more than 100 individual projects and over 3,000 personnel. Edward McCullough has handled over $2.5 million in research from chemical, He's the chairman of the AIAA Space Colonization Technical Committee. He also has been commissioned for $1.5 billion in process equipment for Bechtel. I'm going to ask a series of questions after each panel member gives minutes, a 5-minute introduction to ISRU, and then we'll go through a series of questions. So please, Brad, if you'll begin.
Am I asking the first question?
No, we're going to go through 5 minutes of introduction about what is ISRU.
Oh, what is ISRU? ISRU is a wonderful NASA acronym that I'm sure not everybody in the audience understands. Thank you. I guess we have to get fairly close to these things. ISRU stands for InSitu Resource Utilization. Basically, it's a fancy term for mining your resources in space. My analogy or equivalent to ISRU is put yourself back 500 years. It's the axes, the hammers, and the saws that made colonization of North America possible. These are the tools that we can build a future out of. That's my answer. In space. John, you're up.
So I'm going to come at the question slightly differently. And in particular, in-situ resource utilization is nothing more or less than living off the land. And of course, being able to utilize local resources is the central ingredient to a sustainable and affordable human or robotic presence or ambitious operations beyond low Earth orbit. The exigencies of the rocket equation, dealing with what it takes to move large amounts of material from the Earth into space and around in space and up and down from planetary or lunar surfaces, compels local resupply. And this, of course, is no different than the way the economics of transportation or operations work on Earth. It is unimaginable that there would be the global economy or even local economy the way it exists now, with the ability to pull into a filling station and resupply your vehicle without being able to go into the grocery store and resupply your household, without being able to, if everything that you did had to somehow be brought with you from wherever you started in the morning or in the week or in the month or in the year, everything we do in normal life is unimaginable. And this is the situation we are in now with space activities. All the kinds of things that we aspire to accomplish, the ambitious things we'd like to see possible, are impossible without the ability to utilize local resources. So, Ed.
To me, ISRU is a way to get at materials that you can use for either propellants or for infrastructure at a much lower cost. Because you can launch all of this to Earth. For instance, you space solar power satellite by launching 90,000 ROVs from Earth. But it would be far cheaper to actually send a fraction of that amount of material to the moon to build the process plants and the facilities that could actually take the material that's already at that point in the Earth's gravitational well and transfer it to the location of the space solar power satellite, or for infrastructure in lunar orbit or on the lunar surface at much lower cost. So essentially what it does, disconnects the growth in your infrastructure on the moon, or cislunar space, from the space transportation system. Meaning, instead of being able to develop infrastructure mass in a linear fashion, which is what would happen if you use your space transportation system, you can actually have it start to grow in an exponential manner. We don't want to actually send a whole city full of mass up on ROVs to go to the moon or Mars. We go there and use the material that's already there. We already have industrial processes we've been working on for these types of things for thousands of years. There is a process called a carbothermal reduction of iron to produce oxygen that's more than 2,000 years old. So these processes aren't all new. Some of them are. But some of the processes you hear discussed regularly have been around for over a couple of thousand years. So as far as the chemical engineering community, these are processes that we can do. And a number of people have done studies on them. And you can look it all up in the literature. There was the Space Engineering Research Center at the University of Arizona, et cetera. And so there's a broad literature on it. ISRU will disconnect your infrastructure growth rate from the space transportation system.
Thank you, Ed. You touched on this question, but the first one we're going to go over is, what might lunar ISRU make possible? Brad, would you like to start?
Colonization, settlement. Yeah, I guess to follow up on my analogy of 500 years ago, imagine loading every boat that came over from Europe to America with building materials, food, and making everybody who lived in North America depend on the food and building materials to maximize their growth and settlement of this.
Yeah, to Europe to get more when you need it.
Yeah. Settlement. We got to learn how to live off the land. We have to learn to utilize the building materials that are already in space. You decompose that lunar soil, you get a variety of useful metals, you get oxygen, you can make glass out of it, but Ed knows more about that than I do, so I won't steal his thunder.
So I'll take that question in a slightly different direction. What might ISRU make possible as opposed to lunar ISRU? And in particular, I think it's a fairly reasonable argument or fairly plausible argument that, with the possible exception of the moon, or of Mars, that ISRU is either enabling or is tremendously valuable for sample return missions from across the system. If in fact you have to take all of if someday there's a hope to bring back samples from some of the outer planet icy moons, and from the surface of those icy moons, then the ability to locally manufacture propellants is probably a very valuable capability. Similarly, and I suspect Ed will also touch on this, but I'll bring it up now. Similarly, for the moon and for ambitious lunar operations, the ability to refuel transportation systems going to and from low lunar orbit or from the Earth-Moon libration point, L1, would be tremendously valuable in making possible a high efficiency and low cost transportation system to and from the lunar surface. And so in that regard, I think ISRU will make possible, from the standpoint of the propellants, quite ambitious scenarios on the moon and across the solar system, which wouldn't otherwise be plausible.
Okay, first let me say a couple of things about the propellants. NASA about 15 years ago was looking for about, I believe it was 750 metric tons of oxygen per year, or 650 or something like that. And there was a lot of development work going on process plants to actually produce for the moon. Now that we have the possibility of water being at the poles, we have much less of a need to bring hydrogen to the moon in order to make the propellants. So the situation is better than it was like 15 years ago, when the case didn't close very well for using the lunar locks, because you had to actually bring hydrogen from the Earth with large tanks, et cetera, and it was a diminishing return type thing to do that. Now, as far as the other things that you can do with ISRU on the moon, if you take a look at this chart right here, there's one column that says material class. And what you'll see in there are, those are the types of materials that you need in order to build an infrastructure. We have structural metals, we have reinforced metals, we have thermal materials, refractories, glasses, fibers, electrodes, magnetics, etc. Once you have those types of material in stock form, then the industrialists can actually go in with robotics and other things and start putting the infrastructure together. And I say this is what you need to do in order to build the lunar bases everyone keeps making airbrushed pictures of. You won't get a lunar base like that unless you have these materials there to actually build the infrastructure. So what ISRU can do for you is it can actually give you the kind of things you have here, minus, for instance, the volatiles, the things you can produce with volatiles, because all of these things are all relying on the 7 materials or metals, or should I say the elements that are available everywhere: calcium, magnesium, iron, silicon, oxygen, and aluminum. We have found out that in the polar craters we have frozen volatiles. It might turn out that there are a lot of volatiles there that we can actually use to even bring in a plastics industry, et cetera, but for right now, that's not in the works.
Thanks, Ed. Next question we're going to ask is, what are the current barriers to ISU? What can be done to surmount those barriers? Who will begin?
Wow, great question. I guess jump right in since I've got a big list here. I guess I would characterize 2 classes of barriers. First class of barriers is related to government implementing an ISRU program, and I won't speak to a specific government, but I think you know which one I'm talking about. The second class is private development of space resources, and I'll tackle that one first because it's always easy for the government to say, well, if that stuff is really commercial, then you guys should go off and do it and don't bother us. So it's not commercial. It may be commercial at some point in time. Clearly a barrier to ISRU is markets, people who are ready to accept the products that are made. We don't have people living on the moon yet. There are no customers there for lunar materials, building materials. There's nobody landing there. There are no customers for propellants. So, that. It's a chicken and egg situation. Another barrier to commercial development, and again, I'll parrot what David Livingston was saying earlier. I'm in partial agreement with that. The other barrier is property rights, and that is something that government can influence, the development of a property rights regime for space. Now, what do property rights enable? Some people would call it speculation, land speculation. I guess what I would say is, I draw upon an analogy. I'll keep it very simple. Canadian mining industry often buys prospects from people who have property rights plus geologic information. Those are tradable in an open market. You go down to the mining association meetings, you can build a little company and put it on the Toronto or Vancouver Stock Exchange, and all you have is geologic information plus property. The potential in the future to make money mining and selling a mineral resource, a commodity, okay? That's not that different than what we have in space. We have the geologic information for a lot of this stuff. What we don't have is the property rights, and that stuff can be traded, and we can establish a market value today for what the market really thinks that stuff is worth. But we need government to act on the property rights thing. Now, addressing other government programs that may influence ISRU, without naming any names, certain decisions like going to hypergolics for a lunar lander strongly influence the viability of ISRU by pushing it farther and farther away from the near term in terms of implementation in an architecture. A certain government space program is rather reluctant to embrace ISRU and bring it in and make the big decision, which is take the lower stage off the lander. That has a propagation effect through the entire architecture. If you were to develop ISRU robotically as a government space agency, and who knows, perhaps a government space agency somewhere in the world today might do this, take that risk to develop an ISRU plant, an oxygen and hydrogen source, go with the choice of optimal propellants from the moon, which is hydrogen and oxygen from the water, possibly methane if you want to add some more energy and oxygen, and then design a system that's a single stage refuelable lunar lander that propagates all the way back, and guess what it knocks over? The heavy lift launch vehicle. We can do it with this with the ELVs today.
John?
So hopefully, I'm going to manage to say something that have already been said by Brad or will be said by Ed. I'll certainly try to, so that the panel doesn't become redundant. So what are the current barriers? Well, clearly, one barrier which Brad alluded to, which I will reiterate, state slightly differently, are the system design decisions that are made by the major space programs, major space agencies. If system design decisions are made that in and of themselves preclude the introduction of in-situ resources, then that is a significant barrier, both a technical one and a financial one, to the later introduction of those in-situ resources. Another barrier is that, obviously, of energy. You have to have adequate and appropriately tailored energy supplies in order to make an ISRU plausible. And that includes energy for both mining and extraction and beneficiation, or extraction of the what we hope are the volatiles to be found in the dark locations of the moon, their processing, separation, electrolysis, liquefaction, storage, transport. All of that's going to take energy. And if the energy is $50 or $100 a kilowatt hour, it's unimaginable how ISRU ever makes sense. So energy is important. Another is a concept of operations. I've seen some remarkably implausible CONOPS for how you would use local resources. For example, a presumption that you must have 24/7 utilization and fixed capacity in terms of your ISRU surface capabilities. And because you assumed it had to be operations, then you must have several hundred kilowatts constant power, in which case you must have a large-scale nuclear reactor, which, based on recent cost estimates by the major programs, could be 10 or 15 or 20 billion dollars. And since you don't have that, then obviously you can't have ISRU, and therefore, so it becomes self-fulfilling. So there's a strong need for some more thoughtful and uninfluenced by already existing programmatic decisions, notions of the concept of operations for ISRU that take advantage and live with the circumstances of where you want to do it, such as on the moon having 14 days of day and 14 days of night, or you have continuous sun in some places, and so on. And lastly, I'll just mention an anecdote very briefly. Some years ago at a meeting of the Space Resources Roundtable, the group that Mike Duke organized a number of years ago, I sort of posed a question, which was, how small can you go? So this is sort of the ante, where it's appropriate here in Las Vegas to talk about the ante. I haven't been doing very well at the tables, but that's all right. I enjoy the game. How much do you have to pay to play? If you look at some of the wonderful line drawings, not airbrush, but line drawings of in-situ resource machines of the circa 1980, city-sized individual machines being envisioned as the way you have to start with ISRU in order to have a plausible scenario to build important things. Obviously, if you have to build a city before you do anything, you're never going to get anywhere. And so I posed the question, how small can you go? And the answer appears to be pretty darn small, i.e. not even tens of tons, but perhaps hundreds of kilograms to have sufficient independently operable ISRU with finite objectives, but ISRU machines. And so that's another, I think, barrier is the ante. And so I would suggest that we need to be thinking about how small can we go living within a legitimate concept of operations, for example, on the moon, using energy appropriately and assuring that we have affordable and abundant energy for that CONOPS in order to introduce ISRU systems that have been developed and allowing for their use. Thank you.
On answering that question, first I'd like to comment on two things that John just said. One of them is how small can you go? Well, I was a principal investigator for Resolve to design a magma electrolysis demonstration that could possibly go on the RLEP-2 mission, which is no longer going to go. And our requirements were 10 kilograms, 15 liters, and 80 watts. And we were able to actually design a magma electrolysis plant that actually came out to around 6 kilograms that could actually do that job on 80 watts. It took a long time, you know, it takes 500 minutes to heat up, but you can actually make a magma electrolysis plant this big as a demonstrator. The second thing, as far as the gambling and enjoying the process, is unlike John, I put $6 in the dollar slot and won $3 grand.
No.
That was last Saturday.
Don't tell the hotel.
Now, the barriers to ISRU as I see them, I'm the type of person that actually goes out and builds process plants, and so I'm looking for the immediate barriers of why we're not doing it right now. There was a special action team meeting for the Lunar Exploration Analysis Group that was requested by NASA headquarters, and at that meeting, Brad was there. I was there, and a gentleman named Paul Lucy and I actually co-chaired the breakout session for the lunar polar volatiles and also the ISRU. NASA headquarters people were there, and they talked to us, and they said they know that ISRU is very important, but they just don't understand it. And so my first comment on that would be this: there's insufficient understanding of NASA headquarters personnel on that, and that affects whether or not they select it for the architectures. Another thing is that you have improper funding arrangements for this type of research. Back in the early 90s, what we had, and in the decade before that, we had the Space Studies Institute was adequately funded to do this type of research. And we also had the Space Engineering Research Center at the University of Arizona, I believe under Terry Triffitt was his name, who also did a lot of funding of this kind of research. And it would be quite useful if we had those funding mechanisms back in place now, so we could actually do the same kind of research based on the new information we have on the moon. And the last comment would be, tell you an anecdote. A friend of mine who works for Boeing, I met him at a Joint Propulsion Conference. And this was after we had discovered that there are hydrated minerals on Mars' jarosite. And I said, well, one of the things we need to do is we need to get into the mix here and experiment. Well, we'll go to Mars and we'll take some of this material and put it in a container and heat it up and drive off the water and measure how well it works. What he told me was, and this is where I get in trouble with Mankins and the TRL levels. He told me, well, we can't do that because that's only TRL level 1 or 2. You know, there are other things that are already in the pipeline, so we won't be able to do that for 20 years. And I looked at him and said, are you crazy? We did that on Viking twice. It's TRL level 9. And so what happens is we have people go off and make decisions without doing any kind of homework. And we end up with things just basically being quite chaotic. And we're basically just thrashing around and getting nowhere. So that's my comments on the for ISRU.
Thanks. The next question we're going to ask the panel is, how does ISRU fit into the larger space community? How does it affect the new space opportunity matrix?
I guess I'll tackle that one first again. As an economist, I guess I've learned to break an economy down into production function. My training tells me that you have three major factors in a production function: labor, capital, and resources. Well, last time I checked, there's a lot of labor. People are trying to get jobs with aerospace companies that don't even have enough money to hire them right now, and yet we're going back to the moon. It's a very enthusiastic crowd here. I myself work frequently for peanuts, as an example. My salary requirements aren't very high because I'm an enthusiast. Clearly, we're not lacking labor. Capital. There's a lot of money floating around this community. There's a lot more than there was 10 years ago, or even 5 years ago. And I think more is on its way. $150 trillion in cash, the cash supply globally, worldwide, $50 trillion of cash in the United States, 20 trillion annual economy, or 25, I think, worldwide, something like that. What we lack in is a good story. There's plenty of capital to go around. There's a lot of risk capital, and rates of return are at a time low. So you don't even have to tell that good of a story to get capital. How about natural resources? Well, it costs me $10,000 a kilogram to acquire Earth-based natural resources in low Earth orbit. It costs me $35,000, $40,000 per kilogram to acquire natural resources from the Earth in geosynchronous orbit or out at L1. If I want to use Earth-based resources on the lunar surface, it's somewhere between $90,000 per kilogram to $150,000 per kilogram based on the numbers I've run and what some of my colleagues have run. It's expensive to do things in space unless you use local resources. So if the offsetting cost of an item on the lunar surface is, let's take the minimum, $90,000, $100,000 per kilogram, should I be able to sell my kilogram of lunar soil to someone there who wants to use it for $100,000? $1 million, or 10 million? No, 100 million a ton, excuse me. The resources are there, they're in space. That's the other part of the economic equation that defines growth. Where does it fit within the new space opportunity matrix? These are, I guess I'll keep this one, I hope I'll keep this simple. The example I gave you earlier about Canadian mineral exploration. Let's say that I go out as a geologist, acquire the property rights, acquire some geologic information, and then sell that piece, aggregated bundle, to a mining company for $50 million. Very common transaction in Canada. What have I done? I've gone out, put some sweat, some time into collecting some information, spent a few years out, field seasons, collecting samples, taking them to the assay lab, filed a claim with the Canadian government. It's probably a territorial province, government land, or a few claims. Put some sweat into it, but all of a sudden I've generated $50 million in new wealth. And if that mining company grabs it and buys it for $50 million and makes a $500 million or $1 billion on that $50 million purchase, they've generated new wealth. It's going to be the same thing in space. We're talking about generating new wealth in orders of magnitude more than we've ever seen before.
So the way this question is posed in our cheat sheet that we all have here with us is ISRU fit into a larger space economy. And the point that I would begin with is to recall that the utilization of in-situ resources is not an end in and of itself. It's not unheard of to see or to have seen in the past arguments in which you say you're going to go to the moon. Well, why are you going to the moon? Because resources. Excellent. What are you going to do with the resources? I'm going to use them to allow me to be on the moon more affordably. Oh, terrific. But while you're there, what are you going to do? Well, I'm going to maintain the equipment that does the ISRU. Why do you need to maintain it? Well, so you get the idea. So the notion of in-situ resource utilization becomes an end in and of itself, which it is not. You need to think in terms of primary purposes, primary markets, and secondary. Primary markets, why do we do things in space? Why do we want to do ambitious things in space? I think comes down to essentially 5 justifications, or approximately 5. These include business. We do business in space, things like telecommunications satellites. We do, and this is to serve primary markets here on the Earth. We do things in space to better assure our security. Whole defense programs and defense activities are built around this premise and this need. It's the high ground. We go to space to do excellent science, both space science and earth science. We go to space for policy reasons, for reasons of international relations or international competition. And there are a fair number of folks who hope we will someday go to space for purposes of settlement, to extend the human species, to extend human presence permanently beyond the Earth. And so those are primary purposes. And so in thinking about ISRU, it's important to remember that ISRU is a secondary industry, it's a secondary market, it's a set of secondary systems that have to somehow link effectively and profitably into these primary purposes in the same way that other secondary industries, such as launch vehicles or ground networks and so on, now actively serve and profitably serve in some cases those primary purposes, those primary markets. And so I would suggest that we sort of keep that in mind, and it's one reason why I highlighted a few moments ago how important it was that decisions that are made on the new systems that are going to be built for these primary markets, these primary purposes, support the introduction of in-situ resources. There's a good story that goes back to the early 70s about the formulation of the Space Shuttle program and its concept of operations, and the whole idea of building a spacecraft like the Hubble Space Telescope so that it could be serviced in space. Turned out to be a profoundly good decision given what later happened in the program. It would be just as easy to have envisioned a Hubble Space Telescope program that was not conceptualized, designed to allow for in-situ repair and maintenance, and was not based on a detailed cost-benefit analysis and systems trades and so on. It was a policy decision. We should do this. And it turned out to be a really good decision. Well, the same sort of thing is needed in our systems decisions for these primary markets now, in terms of in-space servicing and refueling and all of those steps that would allow us to later introduce in-situ resources.
I'd like to continue on with some of the things that John said. My simple answer is that ISRU reduces the space transportation requirements. It's much cheaper to build materials or to fabricate things that you need at that level of the Earth's gravity well with material that's already there, instead of lifting it all away from the Earth's surface and adding something on the order of 62 megajoules per kilogram in order to get it up to the moon. If you take a look at this chart again, the ISRU produces what we call millstock materials. This is the very advanced ISRU. This is not what you start with. But when you're talking about what we're going to do in 2025, these are the types of things that you'll be able to produce. These are millstock materials. Think of them as building materials, the hardware store for the moon. The manufacturing organizations or groups will take these materials and use autonomous types of techniques to go build the infrastructure. Now, ISRU came from the requirement to come up with a cheaper way of building space solar power satellites. Those things were studied during the 70s. And when people looked at the cost of launching the material to build a satellite that was 10 kilometers long from the Earth's surface, they decided that we had to find a different way to do that, and they found out the actual delta V from the moon was much lower. And they started working on how they were going to take the lunar materials and get the metals and the ceramics and the glasses and the sheets and the tubes or the powders, et cetera, and the wires to build these space solar power satellites. And so there was a demand for ISRU. There was also a demand for ISRU when people were taking a look at the actual cost of sending propellants to the moon for operations or propellants for a Mars vehicle, et cetera, or even building a Mars vehicle. If you have advanced ISRU, you can get all those things from the moon. So to me, how the ISRU fits in the larger space economy is it's the thing that eliminates massive amount of flights from the Earth's surface.
Brad, you have an additional series of slides. Would you like to explain them to us at this time?
Sure. Let's go with the first one. I guess I hit enter.
Should probably go stand next to that machine.
Aha.
That's much better.
All right. Well, I guess what I wanted to do here was to show what happens to Apollo. I ran a really simple model, used the rocket equation, and assumed certain pieces of the Apollo stack disappeared or shrank based on the availability of fuel in certain places. I assumed there were 3 fuel nodes, one of them in low Earth orbit, one of them in lunar orbit or at L1, and the third one on the lunar surface. So the first step down in the Saturn V sizing reflects the throwing off the stack of the descent stage of the lunar lander. So that's not entirely accurate, but it was an easy estimation to do. Sure, you'd need legs attached to the ascent stage, but as a first order approximation, maybe you'd lose one of the astronauts, I don't know. As a first order approximation, it gives you an idea or feel for what happens to the stack. The second one is launching the command module empty rather than full and losing the descent stage. The third one looks like one of the other stages, I guess, what do we call it, the translunar injection. So you've got sort of your return flight propellant, and then you got your translunar flight propellant. And the fourth and fifth one there are reusing the command and service module along with the lunar ascent stage. So you actually, all you're really launching by the final one is astronauts. So then I assigned based on gross liftoff weight. And you have to understand I'm a mining engineer, I'm not an aerospace engineer, so this is a total approximation. I just wanted to show you, to give you an idea or a feel for what happens. So these, based on gross liftoff weight analogies, these are the rockets from our fleet today that would match that approximate size. You'll notice at the end is Gemini. All you're launching is 2 astronauts to low Earth orbit where they pick up a reusable tug system, they transfer to lunar orbit, get into the reusable lunar lander, go to the lunar base, refuel again, and go all the way home that way. It's a supply chain. The point being, as you reuse, what makes reuse possible? Propellants. This is my argument for where propellants are utilized. So, and again, it's a very crude example, but meant to be informative. So, the next analogy is, again, a very simple one, and it's to show how ridiculous we do rocket launch today. It's my expendable Honda model, and so I thought I'd work the problem from the other side, again, you know, to evoke an image for what would happen if we actually threw our car away every time the gas tank was empty and bought a new car, which is the way we do rockets. So there's my assumption, 12,000 miles a year, et cetera, et cetera. What happens? Oops, hope I didn't press it twice. Well, you can see the stack of cars. Can we go to the next one? Thank you. That's your cost. This is your cost for driving 12,000 miles a year. And this was last year's prices, or maybe a year and a half ago I did this. So I've got all my assumptions on there, and it's obviously ridiculously expensive to drive. And then the final slide is multi-segment. This is what happens if you have to stage cars. So, and again, these are approximations, but you can fill in they're probably not going to be that different than what I approximated. There's your capital cost for getting 500 miles when your gas tank runs out. But if you need to go 1,000, what happens? Let's go with it. Click the button again. You put it on back one, flatbed. And don't you know you pay more for a flatbed than a car, so it's an exponential cost function. Next is a lowboy, and then after that is a train. And you'll notice on the right-hand side I've assembled the Apollo stack. So these are my ridiculous notions for how the analogy for how we do space transportation without refueling. And that, again, that's to tell you where all the propellants are going to go that we're going to manufacture on the moon to get back and forth inexpensively. Earth to LEO is your dominant cost in that, plus operations.
Thank you, Brad. Next, we have, I believe, 5 minutes for questions. Okay.
Brad, very interesting. Thought exercise there, in that last slide, it looks like there's about a 10-to-1 cost ratio under your thought exercise, right? I'm sorry, 100-to-1 cost differential. But if you go back further and look at the different stacks of rockets, in fact, the cost differential of those rockets is only about a 10-to-1. And so what I would suggest is that the cost is not in the rocket, it's in all the infrastructure that we built up to be able to launch rockets. I mean, even a Gemini, although it looks really small on your picture, I mean, that's still a very expensive thing to launch relative to a Saturn V. A Saturn V is not 100 times more expensive than a Gemini. It's probably only a factor of 10 because of all the extra infrastructure that we have in our space program. Just comment on it.
I'd like to defer the question to John Mankins. He and I have had a sort of a side discussion relating to learning curve and production costs. And right now, if I use NAVCOM, NASA and Air Force cost model, to do a cost estimate on a lunar architecture or a Mars architecture, and I assume 10 to 50 units, my maximum savings is about 15%. So I go from 100% to between the 10th and the 50th unit, 85% of the original production cost. But John's numbers are a little different, and maybe they address that ratio.
Yeah, part of the issue with regard to a reusable transportation infrastructure architecture rather than an expendable one is obviously your Earth to orbit strategy, and the point is certainly well taken that in the rocket equation you benefit in going to larger rockets. And at some point you get to the point of diminishing return where to such a small system that it can just lift itself and its fuel. Other than the market forces, it's one of the reasons why the goal of sending 100-kilogram payloads to low Earth orbit has proved so elusive, even though it's been sort of a holy grail of the small satellite community for many years, going back to the DARPA program around around 1990 or so, if not before. The challenge with regard to exploration is that the things that you want to move around in space and the things you want to do in space, like sending more than part of an astronaut down to the lunar surface, are so demanding that you have a lot of flight hardware, and it's expensive. And it's not the $15 a pound or $30 a kilogram the way an automobile is, and it's not $3,000 a kilogram. It's on the order of $100,000 to $200,000 a kilogram for these human-rated systems, of which you're not going to build very many. And I think it'd be interesting to see the same analysis or same kind of series of charts perhaps for 747s and A380s and so on, using those one time, because they're quite analogous in terms of the hardware. I think the basic point that it will be cheaper to get people up and down to space from the Earth, and they rendezvous with all of the equipment they're going to use to go beyond low Earth orbit, and you reuse that equipment because you're refueling it, that's extremely profound and makes a huge difference in the cost of sending high-value cargo like people to and from destinations beyond low Earth orbit. And as long as it's $1 billion worth of lander, every time you go down to a point on the surface of the moon, plus all of the other equipment to do that, it's never going to be very affordable to do it.
Thank you. I'd like to accept one more question, if the panel can keep the answer under 1 minute.
Obviously on Earth, our primary building material is steel, which is hard to make on the moon without carbon. But I was wondering, has there been any work done on using iron on the moon? Would that be a viable building material? Because of course the gravity is only 1/6, so it may be strong enough for most applications.
Yes, the couple of processes that will actually produce iron for you. One of them is
Edward,
called...
if you could
Repeat the question.
let the
Repeat the
questioner
question.
repeat the question.
The question was, are there any viable processes that can actually produce building materials out of iron as opposed to steel? Is that correct? The steel being difficult to get on the moon because there is carbon is a lunar deficient element. The first thing would be is like the question of like, well, how much do you want to produce? Because the actual carbon that's in the steel is a very small amount, like it's 1.5% or something like that. So if you wanted a ton, you would need to have like say 10 kilograms of carbon in order to make the iron into the steel. Yes, you could import that. The other thing is that since we do have an environment that is only 1/6 G, you can actually work with materials that aren't quite as strong. You do have to deal with things other than the static loads. There would be thermal cycling loads, et cetera, so you would have to actually design your systems to accommodate those other kinds of loads, but for the static loads you could use something that was much less. Also, if it didn't really cost you much to make anything, because once you have the processing capability there, if it's operating correctly and it's maintained, it'll continue to make the materials you need. So you might be able to be a little bit more extravagant in your building in order to compensate for the lack of the properties of regular steel.
Brad, John, Ed, thank you very much. If you have additional questions, catch them later on. Thank you.
Okay, so that concludes